Okay, sorry, I was playing with my settings. Today we're going to talk about, we're going to spend 2 days talking about Gibbs free energy and the idea of spontaneous and non-spontaneous reactions and what that's going to mean for the reactions that we're talking about. And last week we talked about enthalpy. Yesterday we talked about entropy. And today we're going to talk about combining those two things to come up with another formula that will help us determine whether or not a reaction is spontaneous. So I'm going to share my screen, my PowerPoint with you. Okay, here we go. Now, we're going to call this the free energy change. And as we come down the notes, we'll give you a formula for using this, and it's going to, because of the person who came up with it, of course, we're going to call it Gibbs free energy, and that's going to be a formula. So a couple of things to keep in mind. You need to understand that reactions are most favorable when they are exothermic. Okay. They want to decrease the enthalpy, which means they get more negative. Okay. And when they increase the entropy. Remember, the whole tendency of the universe is to go from orderly to disorderly in a simplistic way. Okay. So we want to, a reaction that is most favorable increases the enthalpy, or decreases the enthalpy, and increases the entropy. So we just spent a few days talking about enthalpy and entropy. So how can we use those to help us determine whether or not a reaction is likely to occur? So we're going to take those two things. We're going to combine the effects of change in enthalpy and entropy for each reaction we talk about. Okay, so you can have, since we're dealing with the idea of enthalpy and entropy, and we know that entropy and enthalpy can be positive or negative, then we really have 4 combinations of types of reaction processes that we can study. So we can have an exothermic process with increasing entropy, and that would put in shorthand using our symbols, that would be a negative delta H with a positive delta S. So a negative enthalpy, exothermic, positive entropy, increasing entropy. Okay. We could have exothermic with a decreasing entropy, which would mean both of the overall signs for a reaction are negative. Then we could switch to endothermic, and with endothermic, we could have increasing entropy, so 2 positive signs for increasing entropy and an endothermic reaction. Or we could also have an endothermic reaction with a decrease in entropy. So there's 4 different combinations that the equations that we study can do. And depending on how negative and how positive, it's going to indicate whether or not the reaction can proceed. So let's talk about this free energy idea. The free energy of a reaction is the combination of the change in enthalpy and the change in entropy. And we're going to throw in the idea of temperature with it too. So this idea of Gibbs free energy, we get a G there. Okay. The free energy change, a change in free energy, is going to be the delta G symbol. So here's the equation you're going to use. It's no longer just products minus reactants. It's going to be a combination of those. So we're going to take the change in enthalpy, which is the sum of all the enthalpies of the products, minus the sum of all the enthalpies of the reactants. That's your overall delta H. That's what we spent kind of the first part of the chapter talking about, along with specific heat capacity. We talked about enthalpy. That's that delta H where you took the products, added them all up, subtracted from those products the reactants after you added all of them up. All right. Then yesterday we talked about entropy, and we did the same thing. We took the entropies of all the products, added them up, took the entropies of all the reactants, added them up, and then said products minus reactants give us a value for entropy, and it would tell us whether it was increasing or decreasing in entropy. All right. Now, this equation combines both of those things and throw in temperature too. Now, let's look in your textbook, head back to the chart, and I want you to make sure you remember something. okay? Because in the chart, let me find it, page 352 and 353, I want you to, star this, asterisk, imprint it on your brain that the entropy values, right here, the entropy values, the temperature unit is Kelvin. So when we throw in this temperature right here, T delta S, that means temperature times the change in entropy. So the change in enthalpy minus the temperature in Kelvin times the change in entropy. Because we have to use Kelvin because the units for entropy have been calculated for us in using Kelvin. So make sure if I give you a temperature in Celsius, add that 273 to it, okay? So let's look at this. Delta G is the difference between the free energy of the products and the free energy of the reactants. So you're going to end up getting two different types of signs. You may get a negative and you may get a positive. Here's what those signs mean. So negative, if you get a negative value for your change in energy, what that tells you is that you are seeing a decline in free energy, which is kind of what you want for your reaction to go. Because what that means is if you see a negative delta G, that reaction can occur spontaneously, meaning not really much outside help. If you get a positive value for delta G, that means you're going to see a net increase in free energy and the reaction is not favorable. And we're going to call that sometimes non-spontaneous. There may be nothing you can do to make that reaction go. Sometimes it might mean that you need to add a catalyst, which will be for a chemistry 2 course if we ever get there. Sometimes it might mean you just need a whole lot more energy to get it going, but sometimes it means it will never happen. Like there are no favorable conditions whatsoever and that reaction just won't go. Okay, so there are two ways to calculate free energy. What you can do is you can sum up all the enthalpies, sum up all the entropies, use the temperature that you're told or that you're experimenting with, and you use that equation, delta G equals delta H minus T delta S, and use the equation I just showed you on the previous slide, this one right here. All right. The other way is if you have available the delta G values, if you have a table, sometimes tables don't include the delta G, ours does, and you may be able to use those from time to time. But if the values are given to you, then you can use those. So on a test, on an assessment, I would probably give you two types of problems. One where you are given the values of delta G, and then one where you actually have to go back and calculate the delta H first and delta S first, apply the temperature multiplication, solve for delta G that way. So you're going to need to be familiar with using both. But the table on page 353 does give you the delta G values for many substances, just like they gave you the delta H, just like it, or the heats of formation rather, and just like it gave you the enthalpies for different reactions. So there are 4 different cases, just like we talked about, like with the endothermic positive enthalpy, and depending on whether entropy decreases or increases, those are the 4 cases we're talking about. And those are 4 different types of problems that you'll see. So in one case, I think what I'm going to do is that we're going to talk about 2 of those today, and I'll give you some problems to solve, and then we'll talk about the other 2 cases tomorrow, and I'll give you some problems to solve there. All right, so the first type of problem you'll see is where you have a decrease in enthalpy, but an increase in entropy. All right, so if it's a decrease in enthalpy, a negative delta H, that means it's exothermic. Exothermic reactions with an increase in entropy are always favorable, okay? They're always favorable. They release energy, they increase entropy, therefore the delta G is always negative. Okay. That's case number 1. Now let's look at a problem. Okay. This says calculate the Gibbs free energy change for the following reaction. I should say reaction, not reaction. So let me scoot this over, delete that. All right. So you have silver plus sulfur gives you silver sulfide. It's balanced because we had to put a coefficient of 2 here, and our temperature is at 298 K. So here is what we're going to do. I'm going to look up and solve for delta S. All right, so what I did was I went and I did so there's a coefficient of 1 here. I looked up the entropy for silver sulfide. So I'm going to go back into my table here and I'm going to look for it just to make sure I didn't make a mistake. So I've got silver sulfide, 144 joules per mole Kelvin times 1. And notice my units, joules per mole Kelvin. Then I have to calculate the delta S for the reactants, and there's 2 of them. And remember, entropy, those values are not 0 for pure substances. Even though these are elemental substances, silver and sulfur, those are elemental form. Entropies, all substances have entropy values. So I'm going to look up silver, make sure I didn't make a mistake. The value for silver is 42.6 joules per mole Kelvin times Kelvin, and there's a 2 there. So I have to multiply that value by 2. Then I'm going to, again, double check, look up sulfur just to make sure I didn't make a mistake as I was solving this for you. 32.1 joules per mole Kelvin, and there's 1 in the balanced reaction, so I have my 1 there. When I take 144 and subtract it from 2 times 42.6 plus 32, I get an overall entropy value of 26.7 joules per Kelvin. Now, I'm going to go ahead and tell you that I didn't calculate. I didn't calculate for you the enthalpy. I showed you how to do the entropy. The overall enthalpy though is negative 32.6 kilojoules per mole, and I did it the same way. Products, some of the products minus some of the reactants, and this one's pretty easy because for enthalpy, remember, pure substances are 0. So all I had to do was look up for silver sulfide just to make sure. I will check that out for you, make sure I didn't make a mistake. And it's negative 32.6. There's a coefficient of 1, so I don't have to multiply it, and I would just be subtracting zeros. So that's why I didn't draw all that out for you. Okay, so with that, I said 30, I'm filling into my Gibbs free energy equation now. Negative 32.6 kilojoules per mole minus the temperature, 298, and it's in Kelvin. Let me just go ahead and put that in there. Times the change in entropy, which I just calculated down here to be 26.7 joules per Kelvin. Now I'm hoping you're wondering, kilojoules here, joules here. I need to convert. All right, so here's what I did. To fill in all my unknowns, I put negative 32.6 kilojoules minus 298, and then I converted this value, 26.7 to kilojoules by dividing by 1,000. And when I did that, I moved the decimal 3 places over and got 0.0267 kilojoules per Kelvin. All right, and that equals negative 40.6 kilojoules. It's negative, negative, negative. If you want a good outcome for your reaction, you want that Gibbs free energy to be negative, and that's what we got. This reaction is spontaneous because delta G is negative. This reaction would likely occur. All right, that's the one type of problem. So that's case 1. Case 2 is when you have a decrease in enthalpy, so it's negative, exothermic, but also a decrease in entropy, which isn't so favorable because remember, entropy has a tendency to increase all the time. The universe is constantly increasing in its entropy. So if you have a situation where you're going to decrease in entropy, that may not work so well. So an exothermic reaction, that decrease in entropy, it depends on the temperature. It may or not go based on the value of the temperature where you're doing the reaction. So it will work if you can continue to use, because remember, a negative entropy would be, remember to think about the equation, delta G equals delta H minus T delta S. So that temperature is going to have to be low enough to offset that negative value of your delta S. Okay, so the delta G is negative only at low temps. Okay, so it's spontaneous only if the temperatures are low, and low is relative. It depends on the entropy and depends on the enthalpy as to how low that temperature needs to be. Okay, so let's look at one. Let's see here. Again, remember I said low is relative. It all depends on how much you have to overcome in order to get a negative delta G. So let's look at what I'm saying here. All right, we have iron. Now look at this. This is a 1.5. I hate, this is where your book laid this problem out. I always hate negative coefficients. I would have actually rather multiplied everything by 2, but I'm just going with the example the book gave you. So as we talk about this, so if you look at this, iron reacts with oxygen to give you iron oxide, and the temperature is 298. Now you say that's not low, but you can already read down here that this reaction is spontaneous. So what does that mean? Well, the idea is that the temperature is low enough to overcome the negativity of the entropy. All right, so here's what we're going to do. I already gave you the delta H formation, because here's why I didn't show you that calculation again. It was an easy one. I just had to look up iron oxide, because this is 0 and this is 0 because they're elemental forms. So I didn't have to subtract anything other than 0. So I looked up the delta H, the formation of iron oxide, and I got negative 824 kilojoules just from the table. I mean, I'll make sure, it's probably a good idea to double check. Yeah, negative 824.2 kilojoules per mole, and I only have one of them. All right, now I do need to calculate the delta S because there's never a 0 value for delta S. Everything has entropy. All right, so I'm going to take my product, which is iron 3 oxide. I'm going to look up the entropy value for iron 3 oxide, which is 87.4, and I'm going to multiply that by 1. You can see here, I multiplied it by 1. All right, then I'm going to subtract the reactant. So I have 2 for iron, and I looked it up, it's 27.3 joules per mole Kelvin. And then I had to multiply 3/2 by 205.2 because that's the entropy value for oxygen. When I do that math, being careful not to make silly parentheses mistakes on my calculator, I get negative 275 joules per Kelvin. So you'll see there's that negative sign. So I have to wonder if my 298 value is low enough to overcome the entropy value. So let's take a look and see what happens. Now again, this is joules. Up here, the units are kilojoules. If I'm going to subtract them from one another, I have to get the same unit. So I'm going to convert 275 to kilojoules. So when I do that, I'm going to take negative 824 kilojoules minus 298 Kelvin times negative 0.275 joules per Kelvin. All right, that equals negative 742.3 kilojoules. So it's negative. What does that mean? It means it's favorable and it's spontaneous. So just when you talk about the idea of low temperatures, it's a relative. That's why they don't say they don't have a certain number that has to be below a certain value of temperature, because it just depends on the other factors like the entropy value and the enthalpy value and how exothermic it is compared to how low the entropy value is. It all factors in because you can have a very, very exothermic reaction. Like this one is pretty exothermic, negative 824.2, and that can overcome a lot for the entropy side. Okay, so I'm going to stop there. I'm going to assign you some problems that deal with these first two cases. So I'm going to give you a couple of problems for to practice on where you have a decrease in enthalpy and an increase in entropy. And then the other case where you have a decrease in enthalpy, so it's exothermic, but you also have a decreasing entropy value. So a couple of problems with those, just to see how this goes. And you'll need to determine, depending on whether the delta G is positive or negative, whether the reaction is spontaneous or not. Okay, and then we'll finish up this chapter with just a few other scenarios tomorrow. Okay, as far as tasks, we're probably looking at Monday, but I'll get back to you on that once I look through the rest of the stuff. All right, I'm going to stop this recording now, and I hope you guys are doing great, and I will hopefully see you in office hours.